This is my daughter, Emma. All right, let's give it a shot here.
Emma, where's your fork?
You hear it?
Where's your fork? Emma, what happened to your fork? Emma, where's your fork? Emma, what are you eating for dinner? Pasta. Is it good? And what are you using to eat the pasta? A fork? A fork, yeah. Where's your fork? There it is.
Did you see it at the beginning? It was there the whole time.
Was that funny?
Can you show us how you can use your fork? Can you show us how you know how to use a fork? Very good.
Remember how Grandma showed you?
Keep it up. That way, that's right.
All right. We got lots more. Maybe on another day we'll play another one. We tried. It didn't go viral. Didn't quite make it. All right, we're going to start here. So let me just... Okay, so just to kind of announcements here. So today, half of you will take the Recitation Quiz, which I posted, I think, Wednesday night. Let's see. And then the web work has been open, but it's due Monday morning. So it's the same ones due Monday morning. And then Monday, people, you'll have your quiz. Okay, we're getting started. Okay, and then I posted written homework last night, due Wednesday. So we're going to have written homework due on Wednesdays. So I posted that in the Mondays section, so you know it ahead of time. And then there'll also be a short web work due Wednesday morning. Okay? Any questions about stuff like this, administrative details? Okay. So I think we left off last time with this example, so I want to kind of pick it up there. So we found the equation of this line, did we not? Let's see how I can do here. Let's do low. Good for a second try. I think we found the constant rate of change was 2.4. And so we worked on this process, but really, that's supposed to be a line, by the way. Okay, so really we say old y equals, or new y equals old y plus change in y, right? What's the old y? If we use this point here. And we got the change in y by doing, using constant rate of change, right? Change in y was our constant rate times the change in x. So really, once we've got that process down, change of x, change in y, and then we can just now kind of do it all in one step if we understand all the pieces, right? So old y equals, or new y, sorry, equals old y plus change in y, and the change in y is calculated by k delta x, right? And our delta x would be x minus 2.9. So we're really talking about this point here, say xy. Which point is that? Which point is that? What point is xy? Yeah.
It's the number, the length of the candle before it started to burn.
No, I'm asking. Well, I'm asking about. Oh, so you're saying it's this y-intercept here, or something like that? Well, actually, the candle one was the problem before. But are you saying it's the y-intercept?
Yeah.
Okay. Is xy the y-intercept in this equation? Y equals yada 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 x. What is it the y-intercept? You're saying it's the y-intercept. This is an important question. What is xy? Yeah. Any and every point on the line. That's what it is. So with that equation, we represent the whole line. Where xy is, this is any point on the line. Because if you put so come along here, we've got an x here. Say x equals 6. Not b, 6. So if I put x equals 6 into that equation, I'm going to get a value of y. Which value of y will it be? I'm not asking for the number, but what will the meaning of that value of y be? It'll be the corresponding y value of that point on the line. 6, comma, whatever you get when you put 6 in. So yeah, so when you write the equation of the line, you're representing every point on the line. You're representing every point on the line. Okay, so I'm gonna put a application to this. We'll do this in blue. Okay, so I want x to be the time in seconds since the camera started moving. And y is going to be the distance in meters to the right of the left basket. What am I talking about here? What's that? Basketball? Okay, but then what are my quantities? What's going on here? What's the situation? Yeah.
Seeing how far the camera is away from the basketball.
Yeah, so given the amount of time, how far the camera is. Have you seen these cameras at concerts and sporting events on wires or on like long arms that zoom around and take really cool shots of whatever event it is, right? Okay. So time in seconds, so x is our time in seconds since the camera started moving. That's our x quantity. And then y quantity is the distance in meters to the right of the left basket. So we're looking at the court, the left basket's over here. So that's our reference point, and we're saying how far to the right is the camera. So does all of this graph make sense in light of those quantities? Does all of this graph make sense? And if not, do we need to restrict it? Any of it not make sense? There is some of it that doesn't make sense, which would be? Yeah, time can't be negative. So is that what we're going to say? Yeah, so we want x to be only greater than or equal to 0. So we're going to chop that off like that right there. And then what about the fact that what's going on here? Does it make sense in this situation? Do you remember what we got last time for that? Did we solve for that? So that was the point 0, negative 1.8. Did I hear that right? Thank you. Does it make sense? 0, negative 1.8, or the fact that this line is in negative y territory at the beginning. Did you say yeah?
Yeah.
Why?
It can be to the left of the negative. It can be to the left of the left pass.
Right. So yeah. So if we're saying that distance to the right is of the basket is our reference point, and that's positive going that way, well then we can just say negative is to the left of the left basket. Perfectly fine. So it starts at time equals 0, starts almost 2 meters to the left, and then which way does it go? Goes to the right, right? And it passes in front of the basket at one point there where y equals 0, and then it just cruising along. So how is it moving? How is it moving? What's that? Yeah, so we got constant rate of change. So that constant rate then is what about the camera? So that the constant rate that we found, 2.4, what is it about the camera? What does it mean? How fast, right? It's speed. What are the units on it? Meters per second. Meters per second. Okay, and what is our formula for speed? Distance over time. So let's try this out here. So this ordered pair right here, is 2.9 a time? Is that a time? Is 5.16 a distance? Okay, same with this point, a time and a distance. So I want you to do distance over time for this point and this point. Do distance over time. Go. So find distance over time for each point and see what you get. Anybody got the first one? $1.78? Cool. Distance over time. And what about this one? 0. I'm sorry, 2.05. Reactions. What's going on here? So you said distance over time was speed. So the speed is 1.78 and then the speed is 2.05? Is it right? Is the speed of the camera changing or staying the same? Is it changing? No, it's not changing, right? It's moving at a constant speed. Why are we getting these changing values for speed then? What's that? Oh, he's talking about the change in distance over the change in time. Is he onto something? Remember the flag example? Remember, it was constant rate of change that the flag was coming down. But we came over and we tried looking at the height divided by the time. The height divided by the time. Was that ratio constant? No. So just because you have a constant rate doesn't mean that the ratio of your quantities themselves stays constant. Here's another example of that. So distance over time is not the speed. Let's refine our formula here for speed. What is speed? Change in distance over change in time. Okay? And so that is exactly the same as what? Delta y over delta x. And that's our 2.4 meters per second. That's our constant rate of change. In this case, the constant rate of change is the constant speed of the camera. 2.4 meters per second. Now, if you took any 2 points in that line, and you did this, you'll always get 2.4. And there's our constant speed. But if you take actual distance values and time values, not constant. That the ratio is not constant, because that's not how we measure speed. We measure speed as the change in distance over the change in time. Make sense? Okay, speaking of speed, it's video day. More videos. Ready? You'll just have to listen to mine.
Der Saxophon ist der schnellste aus den
Let's get a good view here. There we go. All right, so what did he do? He ran. How far did he go? 100 meters. And this is the fastest man alive. Okay, and this is the fastest time the 100-meter dash has ever been run. 9.58 seconds for 100 meters. 20 years ago, breaking 10 seconds was amazing. 9.9 or 9.5 20 years ago was so this is insane, right? So how fast did he run? How fast did he run? Figure it out. How fast did Usain run? It's really small. I guess it's big enough for you guys. Okay, so Usain Bolt broke the all-time world record in the 100-meter dash with a time of 9.58 seconds. How fast did he run? So we had just figured out that speed is calculated how? Change in distance over change in time. What's this change in distance? Change in time? And you guys got 10.44. Is that right? Okay. So I've reproduced the race here. So this is a no. Where'd you go? Yeah. So fast you went, right? See if it works now. There it goes. Okay, so this is reproducing that race. Okay, so it's trying to mimic how he ran the race. And you said, how fast did he go? What does that number mean? 10.44 meters per second. What does that number mean? Every second that went by, he went 10.44 meters. Is that what that number means? Is that what he did? Every second that went by, he went 10.44 meters. No, so you were right. That's what that number means. That number means every second, the distance changes 10.44. Is that what he did? In the first second, did he go 10.44 meters? No. More or less? He went less in the first second. Towards the end, in those seconds, more, less? He went more. So how many speeds did he go? Just ignore that 3. I was trying to do a countdown thing, and I didn't have time to finish it. So how many speeds did he travel in his race? Infinite number, right? Because he starts from 0. He gets up to his top speed. Somewhere along the line, he crosses that speed of 10.44. But at the end, he's going faster. Beginning, he's going slower. So we calculated his speed, but then it's not his speed, except for maybe at a moment. So what's going on here? What is this number about? Okay, some of you are saying average. Okay, so is it we summing up a bunch of speeds and dividing by the number of speeds like you'd find a test average? No, it's not that. So average is kind of a very unfortunate choice for this concept, okay? The word average, because average, you think of arithmetic mean. You think of taking all your test scores, dividing by the number of tests to get your average, right? Your arithmetic mean. But this is different than that, okay? Look at that. This is something different, this 10.4 meters per second. So he's traveling all these different speeds, but yet we calculate his speed and we get just one number. So we want to make sense of this, okay? So while I take attendance, I got some, so let me help you make sense of this here. I have a new runner to join him, okay? Maybe. Darn it. Okay, so I have a second runner to come along, maybe. There we go. And join him. Who's that? It's Emma. Who's going to win? Oh. Okay, so watch carefully. So you watch his race and you watch Emma's race, okay? Ready? Oh, darn it. Go. Okay, so I'm going to take attendance. I got some questions for you here. We're trying to make sense of this number. If he ran all these different speeds, but we used change in distance over change in time to get this number 10.44, a single speed, how can we make sense of that single speed representing something about Usain? Okay, and so Emma's there to help you with that. So can you read those questions big enough? I can make that bigger. Hold on. How about that? Better? Okay, so you study the animation, go slowly through these questions, and I'm going to take attendance. Okay, go. What distance did Usain travel? 100 meters. How about Emma? They both traveled 100 meters. Okay? How many seconds does it take Usain to travel that distance? 9.58. What about Emma? 9.58. There's a point to this, okay? So they both what? They both traveled the same distance in the same amount of time. What was Usain's average speed during the race? 10.44. What's the point of showing Emma? She's staying at a constant rate. What was someone over here saying? He ran different speeds, but she, constant speed. What constant speed did she run? 10.44, you see? So that number, 10.44, since it's just one number, what kind of speed is it? A constant speed, right? So we just have, and that's what Benji, is that right? Is that Benji? Yeah, that's what Benji said. He said every second, 10 point, that's what that number means. Every second you travel 10.44 meters. It's a constant speed. It's a constant speed. So now we're getting to the idea of average speed. What is average speed? First and foremost, it's a constant speed. You get one number, so it's a constant speed. Which constant speed is it? So now, looking at those first couple questions, what constant speed does Emma run at? Okay, 10.44. But this is really about who? This is really not about Emma. It's really about who? Usain, right? It's about Usain. So 10.44. Usain's average speed is the constant speed to do what? Travel 100 meters in the same amount of time. It's the constant speed to go the same distance in the same amount of time. So it's not adding up a bunch of speeds and finding the average, the mean. It's a constant speed that achieves something. It goes the same distance and the same amount of time. This is a really important idea. So why is Emma in this race? Emma is to show us She's a representation of Usain's average speed. She's a representation of Usain's average speed. I keep hoping she's going to win. All right. Any questions on that? So this is very, so in real life, do most things go at changing speed or at a constant speed? Do most things go at changing? Most things in real life go at a changing speed. Yet we use this formula, the change in distance over the change in time, and what happens? We get one number. We get a constant speed. Yet that thing was moving at a changing speed. So this is really important when you're talking about calculating the speed of an object, that to know that you're really calculating this constant speed to go the same distance in the same amount of time. Okay, let's look at another situation here. So we're going to look at, first of all, let's turn that off. So we're going to look at two new quantities here. We got x and y. So x is going to be, say, time in seconds. Since Scooter left the sidewalk, say. Y is going to be, oh no, this isn't right. Time in seconds since we started stopwatch. Okay, y is going to be the distance in feet from the sidewalk. Okay, so we said that this class is all about quantities, first of all. So we've got variables to represent our quantities. How did I do at defining these variables? We're going to keep practicing. We've got to keep practicing this all semester. Again, students who succeed in this class are the ones who can define quantities well and then keep track of them throughout the problem, right? Keep track of the quantities throughout the problem as they change together. Okay, so how did I do at defining those variables? Remember your three criterion? So don't forget. So first criterion is what? Okay, that's number 2. Be specific is number 2. It's got to be, and with distance and time, we always have that reference point, right? With distance and time quantities, we always have that starting. Units was the third thing. Yeah, it needs to be a quantity itself, right? So watch out for things saying like C equals chairs, right? Or S equals students. Those are objects. You need the quantity. You need the quantity associated with it. So I've got time and distance quantity. I've got my units, and then I've got my reference points to be specific, right? Since starting the stopwatch, distance from the sidewalk, okay? So x is our horizontal axis. So as time goes by, there we go. So as time goes by, we think about that time increasing and taking on that x value, taking on many values. Okay, on the x-axis, it's really small. Those are just units, whole numbers. On the y-axis, those are by tens. Okay, so those are by tens on the y-axis. So we think about the quantities changing, right? So we've got our time quantity. It increases after we start the stopwatch. And then likewise, as the time increases, we have the distance from the sidewalk. That's our y value. And so, say right here at 2 seconds, we're some distance, looks like maybe 11 feet from the sidewalk after 2 seconds. And that gives us a point, right? Gives us a point. And as time increases, distance from the sidewalk changes. And we can pause at any time. Here's 5.8 seconds. Corresponding distance about 60 feet from the sidewalk. Nice fast scooter, right? It gives us a point. So then we can think about a graph emerging from all these points, right? A graph is just a collection of points. Not that graph. I want 4. There we go. So we can think about as time increases, so does the distance, and we get all these points. And that creates a graph. So we think about this graph emerging as time goes by, and we're building this set of points that represents the relationship of the distance and the time. Okay? So this distance relationship is given by d equals, or y equals, right up here, 1.5x squared plus x plus 3. So given any amount of time since we started the stopwatch, this formula will give us the distance in feet from the sidewalk by plugging in that value. So that's what that formula tells us. And that results in this graph showing the relationship of those two quantities. Okay, so I'm interested in starting at t equals 3, a starting time of t equals 3. So t, say initial, x, we're using x and y, x initial of 3 seconds, going to 7 seconds. So I'm setting up the scenario here. We're going to look at as x changes from 3 to 7, or the time changes from 3 seconds to 7 seconds. So x final, 7 seconds. Easy question. What is the change in time? What's the change in time? How many? 4. Remember we did this second day class. Delta x equals final minus initial or initial minus final? Final minus initial. Don't forget that. That's an easy thing to mess up. So we're investigating, we're going to look at this change in time of 4 seconds, starting at 3 seconds, ending at 7. I want to know what the corresponding change in distance was over that 4-second period. So I've got my change in x of 4. What's going to help us get distance? So first of all, let's represent that. So here's our point 3. How can I represent that change in time, first of all? Here's that point 3 seconds. Horizontal line, right? We worked on this. A horizontal line, because x is the horizontal quantity, a horizontal line starting there, going to there. And you told me that delta x was what? 4 seconds. From x equals 3 to x equals 7. So this is how we can show a change in time, right? Now I'm interested in the change of distance corresponding to that change in time. I've got my formula. What are you going to do? Plug 4 in, right? We plug 4 into that. It will give us the corresponding change in distance. Agree? What does that, when you put a number into that formula, what number is it think it is? A change in time? Time since starting the stopwatch. So if we put 4 in there, let's do it. So we're going to put 4 in. Y equals 1.5 times 4 squared plus 4 plus 3. What does that formula give us? What is it? What's the meaning of the number that it's going to give us? Yes, sir.
The distance being covered as 4 seconds in the first 4 seconds.
In the first 4 seconds, right? Starting from when we started the stopwatch. Anyone got that number? What is that? 33? 31, thanks. What is 31 feet? See, the y when x equals 4. So right here is x equals, I'll do red. So that's x equals 4. If we plug 4 into that formula, it's telling us the y coordinate of that point, which is 31. Does that have anything to do with what we wanted? You see, it's totally different. It's totally different. So when you're using a formula, you got to know what kind of value does it want and take and use, and what kind of value does it give you then, right? So if that's not it, I want to find the change in distance starting at 3 seconds, ending at 7 seconds. So I want to leave you to figure that out. Is that you're going to tell me how? Yeah. You guys figure it out. I'm going to finish attendance, okay? So find this actual change in distance for those 4 seconds from 3 to 7. How am I going to, I'm going to show that represent that. So when the time changes from 3 to 7, how do I show the corresponding change in distance? How can I show that? Eric?
Do 1.5 times.
No, I want to show it first.
Oh, we want to show it first? Okay, well then you do from the 3rd second to the 7th second. You can horizontal one.
Yep.
And then there you go vertical until you hit the point. The distance.
That's my delta y. So this is what we're after. Which we already decided we don't find that by plugging 4 in, because plugging 4 in means 4 seconds from when we started the stopwatch, how far are we from the sidewalk? Totally different than the change in distance over this 4-second period. So Eric, you want to keep going?
Yeah, sure. So in that equation, y equals 1.5 x squared plus x plus 3.
Okay.
We're just going to put the final value, 1.5 times 7 squared plus 7 plus 3, minus 1.5 times 3 squared plus 3 plus 3.
So you plugged 7 in, and what'd you get for y?
I got 64 feet.
So this is the ordered pair, 764, good. And you did what?
1.5 times 7 squared plus 7 plus 3.
Okay, so yeah, we got that. We're good on that one. Next.
Okay, and then minus 1.5 times 3 squared plus 3 plus 3.
And that represents what?
That represents the time that represents the 3rd second and
Right, so we need to get the distance at 7 seconds and the distance at 3 seconds. What do we get for the distance at 3?
I don't know, I just did it.
We have consensus on that?
I was talking about like delta y.
Right, but don't we need this first?
That first flight, no.
Yeah, 83.5.
Okay, so just as a rule of thumb, in a process like this, I'm never going to ask you for the answer. Okay, but it's okay because I think you've been trained that way. You've been trained that way. We want to work. No, it's not. Don't worry. We want to work it through, right? So we want to work it through. There's lots to do here before we get to that number 64. So we want to lay that out. 83.5. Okay, cool. So now to get that change in distance, subtract. Final minus initial. Delta y equals, there's our 64. Units, what's the units? Feet per second. Is it feet per second? We're not done. Hold on, we're not done. Is it feet per second? Delta y? This is just a change in distance. It's just a change in distance over those 4 seconds. So it's just 64 feet. Okay, so now I want you to find the average speed over these 4 seconds. What's the average speed over these 4 seconds? How would we do it?
Divide 64 by 4.
Because?
Because that's the distance over the time. Change in distance.
Okay. Average speed, change in distance or change in y, or change in x, gonna be? What's the units on that? Over those 4 seconds, did the scooter go 16 feet every second? No, again, changing speed. So then what is the meaning of that number? When the meaning, average is a horrible constant speed to go 64 feet in 4 seconds. How would we show that average speed on the graph? How would we show average speed on the graph? Yeah. So that black line that I just drew represents this number, 16 feet per second. It's like another person on another scooter, right? At time 3 seconds, they pass, and they go to constant speed, and then what happens? Our person on our scooter speeds up so that they travel the same distance in the same time. So that second person on the scooter represents the average speed of our scooter rider. Have a great weekend.
Everything.